Then let us start the new chapter, Chapter 4, Equation of State. First, let me talk about the introduction, namely, what is the equation of state? The equation of state is the relations among pressures, temperature, and volume. With a given amount of matter, one variable of pressure or temperature or volume is obtained if the other two are known. So why equation of state is important? The density rho is one of the essential parameters to describe the Earth and planetary interiors. The density rho is specific mass m divided by specific volume v. And volume of matter in the Earth and planetary interior is different from ambient conditions volume due to high pressure and high temperature. Namely, matters at high pressures usually have a smaller volume, and matters at high temperature usually have larger volume due to thermal expansion. Therefore, if volume and temperatures are given, then we can obtain volume using an equation of state. Then we can estimate the density of the Earth and planetary interiors. Let us remember the thermodynamics. In thermodynamics, pressure P is defined by volume derivative of Helmholtz free energy F at constant temperature T. In equation, the pressure P is equal to minus the partial derivative of the Helmholtz free energy F with respect to the volume V at constant temperature T. Equation 4.1.1. The Helmholtz free energy F is defined as the internal energy E minus the temperature T times the entropy S. The meaning of the free energy is the internal energy available for mechanical work. The Ts is unavailable energy for mechanics, and E is energy stored in the matter. From the equation of P equal minus round F over round V at T, P means the free energy per unit volume, or how much mechanical energy is stored in a given volume. So the pressure P is primarily a function of volume and secondarily a function of temperature. Therefore, in this chapter, we first discuss equations of state at constant temperature T, which is referred to as the isothermal equation of state. And please note that the bulk modulus in chapter 4 is always the isothermal bulk modulus. Let us briefly discuss about the pressure increase by infinitesimal compression. Let us consider a uniform compression of a homogeneous body with an initial length of L0. The length of body is changed by delta L due to infinitesimal uniform compression. Then the length change should be proportional to the initial length L0. Therefore, delta L is equal to C times L0. C is constant, and it is referred to as strain in the usual elasticity. Equation 4.1.3. The volume of the body before compression, V0, is proportional to L0 cubed, and the volume after compression is V0 plus delta V, which is proportional to L0 plus delta L cubed, and which is equal to L0 plus CL0 cubed. Therefore, volume change delta V is proportional to L0 plus CL0 cubed minus L0 cubed, which is equal to 1 plus C cubed minus unity times L0 cubed, therefore which is nearly equal to 3C V0, equation 4.1.4. Then let us consider the pressure increase by infinitesimal compression, delta P. It should be approximated to be proportional to the volume change relative to the initial volume, delta V over V0. Why we consider so is if initial volume is larger, the pressure does not increase significantly even though it compressed in the same volume. Therefore, delta P is equal to minus some constant times delta V over V0. And delta V0 is nearly equal to 3C V0 as we saw in the last slide, then which is equal to minus 3C times constant KT0. And KT0 is referred to as the isothermal bulk modulus. And this delta P is pressure increase from 0 by infinitesimal compression. Equation 4.1.5. Next, let us consider the compression to zero volume by assuming a linear compression. So delta V is equal to minus V0. Then delta P pressure increase is equal to minus the isothermal bulk modulus KT0 times delta V over V0, which is equal to minus KT0 times minus V0 over V0, which is equal to KT0. Equation 4.1.6. Thus, the pressure increase is equal to the isothermal bulk modulus. Let us consider this situation using this diagram. The horizontal axis is relative volume decrease, delta V over V0. The horizontal side, left side, is zero compression, and right side is compression to zero volume. The upper horizontal axis is relative volume V over V0. Left side relative volume is unity, and right side relative volume is 0. Vertical axis is a normalized pressure P over KT0, isothermal bulk modulus. Then in the linear compression, without a compression, pressure is of course 0, and which increase to KT0 at 0 volume. Of course, this situation is incorrect against our experience, and more realistic condensed matter shows the compression over this manner. So the pressure rapidly increases with increasing compression. Therefore, the idea that the pressure increase is proportional to the relative volume delta V or V0 need to be corrected. So the delta P, the pressure increase, is always have to consider along the compression path, which is this should be proportional to the delta V relative to the V volume at each time. Therefore, the relation can be expressed using this differential equation. Delta P is equal to minus KT, the isothermal bulk modulus, times dV over V. dV is the differential volume, equation 4.1.7. Then let us integrate the equation 4.1.7. dP equal minus KT times dV over V. If the isothermal bulk modulus is constant, namely KT is always KT0, then pressure is equal to KT0 times the natural logarithm of V0 over V, equation 4.1.8, or V over V0 is equal to exponential function of minus P over KT0, equation 4.1.9. This situation is expressed using this green curve. So this green curve is drawn by this equation, where KT is constant. However, neither linear compression nor constant KT compression reproduces the compression real matters like this. Matters become more incompressible with pressure. Therefore, we need more realistic equation of state. This slide summarizes frequently used isothermal equation of state in geophysics. The first one is second order Boltzmann equation of state, which has this shape, and next is a third order Boltzmann equation of state, which has this shape, and the third one is finite equation of state, and fourth one is Marnard's integrated equation of state. So I will explain these four equations of state from the next section. So this is the end of the section 1, why equation of state, in chapter 4, equation of state.